Okay, welcome to my talk for TQC about bounding the classical capacity of quantum channels assisted by classical feedback. This is work that I've done in collaboration with my co-authors, Dawei Ding, who also goes by David Ding, Sumeet Khatri, Yihui Quek, Peter Shor, and Wang. First paper is something that David and I published a number of years ago. We're going to keep that brief. And we're going to spend most of the time in the last paper and also briefly summarize this middle paper, which was done in collaboration with David, Yihui, and Peter. Okay. So some motivation, the classical capacity of a point-to-point quantum channel. This is a fundamental measure in quantum information theory of the ability of that channel to transmit ordinary classical bits of information. By point to point, I mean that there's a sender and a receiver. This problem has been studied for a while, and we continue to study it this day from both a practical and theoretical perspective. Practical in the sense that we try to figure out actual schemes that can approach the capacity. And theoretical, we try to establish lower and upper bounds on the capacity. Because in the general case, it's still, we don't have an effective formula for the capacity. Why are we interested in this? There is a quantum advantage, even in this task of classical communication. There can be significant gains in communication rates if we employ quantum strategies. And here in this work, we're going to focus mainly on this problem, classical capacity assisted by classical feedback channel, but on the way to getting that result, to understanding that setting, we'll also talk about this more general setting of forward classical capacity of a bipartite channel. Okay, and Shannon was the one who initiated this problem in the theoretical sense of understanding ultimate limits of communication if there's a feedback channel. And his famous result is that feedback does not increase the asymptotic capacity. Okay, so what is a scheme for communication assisted by feedback? Here is a diagram that's meant to depict such a scheme. W is a classical message that Alice would like to send to Bob, such that Bob can try to decode reliably. How can they do it? The red lines are Alice's local systems. The blue lines are Bob's local systems. The green is the classical feedback channel. So the protocol begins by Alice picking a quantum state that's correlated with the classical message she wants to send. And then Bob can send a classical message over a feedback channel to Alice that's correlated with some quantum state at his end. Okay, Alice will then do a first encoding. She'll send one system into the channel and then have another is like a scratch register that you can process locally. So this one she sends into the channel N, that's the channel of interest. And Bob will get a quantum system, which is the output of the channel. And then he'll perform a channel. It's kind of like an intermediate decoding channel that will have an output quantum system and send classical message over the classical feedback channel. And then this process iterates. Alice will have another encoding operation over the channel. Bob will have another decoding operation, etc. And this depicts a 3 rounds protocol. In general, there could be, an arbitrary number of rounds. But anyway, in this diagram, there are 3 rounds, and then Bob tries to decode. The rate of the scheme will be log of the number of messages, which is the number of bits that you need to encode the message, divided by the number of channel uses. So here there's 1, 2, 3 channel uses. So it'd be log of the message size divided by 3 for this case. For the general case, there'll be some number little n of channel uses. Okay, so let's define some more formal things. We'll define what we call n-shot feedback assisted capacity. Here you saw a 3-shot scheme where you're using the channel 3 times. In general, we can have little n-shot, and the n-shot feedback assisted capacity will denote by this. The backward arrow indicates feedback. Little n is the number of channel uses. Epsilon is the error. And we're going to say subject to the scheme using little n channel uses with error no larger than epsilon. It's the largest rate at which it's possible to send a classical message using the channel little n times along with classical feedback. So the rate will be, as we talked about previously, number of bits per channel use. Okay. And then we can do things like this. We take this n-shot definition and, oops, I didn't mean to have a 1 over n here. That's a typo. So discard this 1 over n because we said this was rate already, bits per channel use. So discard this 1 over n. We'll take limit inferior, n goes to infinity, infimum over epsilon between 0 and 1. That's the error. And we get an asymptotic notion of capacity. This is kind of like saying, allow the number of channel uses to be large, and what's the largest rate you can have, and the limit as the number of channel uses becomes large, and the error tends to 0. Okay. The strong converse capacity is kind of complementary to this, where we flip limit superior and this to supremum. And here we're saying, what is the largest rate you can attain? And the limit is n becomes large. Again, discard this 1 over n, that's a typo. And then as the limit as epsilon approaches 1. And one way to understand this is that if your rate of communication exceeds the strong converse capacity, then necessarily the error is tending to 1 in the limit of many channel uses. So the kind of thing that we're interested in is cases in which this usual notion of capacity is equal to the strong converse capacity. If that holds, we said that a strong converse theorem holds, that it means that the capacity is really a sharp dividing line between the possible and the impossible. Okay, straightforward consequence of these definitions, since inf is less than sup, we get that the asymptotic capacity is less than the strong converse capacity. That's what we're saying here. And one important consequence is like, it's more challenging to get upper bounds on the strong converse capacity. So that's an interesting challenge. And if we get them, then it's automatically an upper bound of the usual capacity. Okay, so that's something that we're interested in this work, is getting upper bounds on capacities. So I want to summarize the results of this, what we submitted to TQC. We said we would present 3 different results. We're really going to go only into one of them in some depth. We're going to briefly summarize another result, and then we'll just very, very briefly summarize the 3rd result. Okay, so this is some work that I did with David back in 2015, posted to the archive, published some time after that. The key statement we can make is that if the point-to-point channel is entanglement breaking, then there's a collapse. The usual capacity is equal to the strong converse capacity, is equal to a famous quantity called Halevo information of the channel. Okay, and what is the implication of this result? It's that the classical feedback does not enhance the capacity. So we get a result that's analogous to Shannon's 1956 results. Why is that? Well, the Halevo information rate is achievable without classical feedback. So, you know, that's why this equality implies this latter statement. So what is entanglement breaking? An equivalent notion is that it's a channel for which the choice state is an unentangled separable state. So the choice state is the state that you get when you send one share of a maximally entangled state through the channel. And what you can show is that if the choice state's separable, actually all bipartite states that you send through the channel in this way, where you're sending one share through the channel, that'll lead to a separable state. And so for such channels, they have no ability to generate entanglement or to send quantum information reliably. And they can be understood as a quantum to classical to quantum channel, where the first part is a measurement, giving you classical information, and the second part is a preparation channel, preparing a state conditioned on the classical information measured. So kind of the idea is that since you have this classical process in the middle, that's why the entanglement gets broken with other systems that are not transmitted through the channel. How do we prove this result? We used a tool known as Sandwich-Renyi relative entropy, and we used properties of it. You know, it's a norm, and in particular, there's kind of a additivity of this Sandwich-Renyi entropy when one of the channels is entanglement breaking. And you know, to prove that result, we followed a method of Chris King and Alexander Halevo, where they applied the Lieb-Turing inequality, which is a matrix analysis inequality in mathematical physics, to understand this problem. So that's kind of the main idea, and I'm not going to go into too much. I'm not really going to say anything else about that result. Okay, another result that we have is that the usual definition of feedback assisted capacity is bounded from above by the maximum output entropy of the channel. And that'll describe how we get that result. I'll describe it in a bit more detail. Okay. And so if you evaluate this bound, one thing we can do is with an extra argument, we can get a refined version of this bound. And we can use that to establish for the erasure channel that feedback does not enhance the capacity of the erasure channel. We can also, and this is something we do in the paper, we can modify the bound to apply to energy constrained capacity, which is relevant for quantum Gaussian channels or quantum continuous variable channels. And we can use that result to prove that feedback does not enhance the energy constrained capacity of the pure loss channel, which is a channel encountered commonly in Gaussian quantum information. Finally, the main thing that we'll focus on is the this latter result. So this is something we proved within the past year. And we showed that this quantity called geometric upsilon information is an upper bound on strong converse feedback assisted capacity. Okay, what I want to focus on now is the second main result listed here. So let's summarize the key ideas behind it. What we first do is we take a feedback assisted protocol and we purify it. So what does this mean? Conditioned on the classical values of the feedback, the overall state is pure at every time step. Let's jump back to this diagram that we had. So what do I mean by purify? conditioned on the classical message and the feedback here at this time step, the state in A0 prime and B1 prime is a mixed state. So this, and it's a product mixed state actually, because these are uncorrelated, they're independent to begin with. So we can purify the state here, and we can purify the state here. And then the purifying systems, we can think of them as being down here, and these maps, these channels are not acting on those ones, on that purifying system. Similarly, for this purifying system, you can imagine it being up here, and these channels are not acting on it. Then this encoding, every channel can be purified using what's known as the Stein-Spring dilation theorem. And then even these channels we can purify as well. Okay. So that's the first idea. Every time step you purify, and then condition on the feedback here, the message here, the feedback here, the feedback here, the overall state is a pure state. Okay. So that's the first idea. And then we consider this kind of information quantity, a measure of classical correlation plus a measure of entanglement, actually. If a state is pure and you look at the entropy of a reduced system, that's a measure of entanglement called entropy of entanglement. So we're looking at this classical correlation and a conditional entropy of entanglement. Here we think of W and F as classical systems, like the message and the feedback, and C as a quantum system. Okay, so this is some kind of measure of both information and entanglement at each step of the protocol. Why is it important to incorporate a measure of entanglement? Well, it's known that feedback can actually drastically improve the capacity of some quantum channels. This was shown by Graham Smith and John Smolin. So they showed their examples of channels for which the classical capacity is no more than 2 bits. But then with feedback, it can be boosted to become arbitrarily large, like if the dimensions of the channels become arbitrarily large. So that was a really great result that shows a separation between classical and quantum theories of information. So in order to handle the benefit that entanglement brings, and in fact, in their scheme, they were using entanglement in a way that cannot be done classically. So if we're trying to get an upper bound on feedback assisted capacities, we need to incorporate entanglement in some way. And that's what we're doing here, information and entanglement. Okay. So what we can prove is that this quantity does not increase under the action of a one-way LCC channel. Why is that relevant? Well, if you look at this protocol again, this part is a one-way LCC channel. First, there's an action of Bob, then a classical communication from Bob to Alice, and then a local quantum channel of Alice. And that's a one-way LOCC from Bob to Alice. LOCC is a famous term, but let's just say that it means local operations and classical communication. Okay, that's the second key idea. We'll purify information measure. We showed that it does not increase in the action of one-way LCC from Bob to Alice. And another thing we showed is that under the action of a quantum channel, this quantity, so under the action of a point-to-point quantum channel, it increases by no more than the output entropy of the channel. So using these ideas, like basically, you know, when you look at this protocol, the information measure that we're looking at, it will not increase in this step, it will not increase in this step, and it will not increase in this step. And for this step, and this step, the most that it can increase is the output entropy of the channel. And so that's the key idea, that the information measure can be related to the number of messages and how reliably you can decode them. And then when you evaluate it on the overall protocol, you can end up looking at it in steps. And these steps do not increase the measure, as where these increase it by no more than the output entropy. So that's the basic idea for why the output entropy is an upper bound. And with that, I will move on to switch gears, talk about the third paper for the remaining 9 minutes. Okay. So a key concept that we use is a bipartite channel, and then a point-to-point channel is a special case. What is a bipartite channel? 2 inputs, 2 outputs. This pair of input and output belongs to Alice, and this pair belongs to Bob. And so it's some noisy evolution in general of the states that are input here in these systems. Okay. And what we can do is we can study the capacity of bipartite channels. Here is a scheme for forward communication from Alice to Bob using a bipartite channel, and we're using it 4 times. So you can use local operations that sort of sync up, that link in with the bipartite channel of interest, and then at the final step, Bob can try to decode the classical message that was transmitted. Okay, what is our key idea here? We have a semi-definite program that can bound the classical capacity of bipartite channels. It's believed that computing the capacity exactly is hard. I think there are some results that actually show that it's at least an NP-hard problem when phrased in a certain way. So what we can do is we can bound the capacity using a semi-definite program that we can compute efficiently numerically. So the ideas that we had for constraints with an SDP is, it's kind of like we're comparing the bipartite channel of interest to one that is free. So one that has no ability to create entanglement between Alice and Bob, and also it's free if it's non-signaling from Alice to Bob. Okay, so using those ideas, we can get this upper bound on the capacity. And I should have put the tilde here. This is a strong converse bound. So I'm going to define this quantity later, the geometric Renyi epsilon information. But what I want to show you is an example of a bipartite channel for which we can evaluate the bounds using its semi-definite program representation. So we can apply the bound to a partial swap channel, which looks like this. When the parameter P is 0, it's an identity channel. And if it's an identity channel, it's a product of local channels. And so that has no capacity. If P equals 1, then it's a swap channel. That has a capacity at least 1 bit per channel use, but there's actually a clever way to use a swap channel and superdense coding to get 2 bits per channel use. And so that's achievable, and our upper bound is consistent with that. So it matches what's achievable right here, and of course it matches what's achievable right here. And then this is the curve linking them together. That's our upper bound. And it remains to evaluate a lower bound that represents what can be achieved. And we're very curious to know how close the upper bound is to that lower bound. Okay, so why are these results on bipartite channels applicable to feedback assisted protocols? What you could do is here replace the bipartite channel with a classical feedback channel. That's what we've done here. And then we can replace this bipartite channel with a forward point-to-point channel. So what we do is for every even use of the channel, we replace with a point-to-point channel. For every odd use, we replace with a classical feedback channel. Okay. And then our bound from here applies just by making the B and the A prime systems trivial. Then that's how you get a point-to-point channel. Okay. And this bound is something we call upsilon information. It is a strong converse bound. And we're depicting it for a depolarizing channel. So the solid line represents what's achievable for the qubit depolarizing channel with the polarizing parameter P. You know, in words, the channel is getting noisier as P increases towards 1. And so the solid blue line is what's achievable in terms of Halevo information. The upper bound is our upper bound. And then at this value of P, the channel becomes entanglement breaking. We can invoke the result David and I had previously to say that, oh, in fact, this upper bound is irrelevant. We know that this solid line is the capacity. Okay, I'm running out of time. There's just a few minutes remaining. But the basic idea is we define this semi-definite programming measure. It's formulated like this. As a function of a bipartite channel. And then we use a concept called generalized divergence. So this is some function of states, rho, and sigma that does not increase into the action of a quantum channel. We can define a channel divergence by optimizing the state divergence over all possible input states to the channels. Okay, and then from these concepts, we can define a generic upsilon information where we take the infimum of the channel divergence with respect to all complete positive maps such that the beta measure defined previously is less than or equal to 1. Okay, and a choice that you can make for this upsilon is a distinguishability measure called geometric Renyi relative entropy. So that's what we did in our work. That distinguishability measure has some nice properties, and it allows us to prove what one could call subadditivity under serial composition. So if you take serial compositions of bipartite channels, then the upsilon information evaluated for the composition is never larger than the sum of the upsilon information for the individual channels in the serial composition. Okay, pretty much hitting the time. I briefly touched on the result with David's from some years ago about entanglement breaking channels. I gave some ideas of how this maximum output entropy bound works. At the very least, we define this upsilon information. Should actually clarify that that quantity comes about by taking the limit of this one as alpha goes to 1. Okay. And then going forward, since all we're doing is providing upper bounds, there's a key question of whether the bounds can be improved. What is going on with the depolarizing channel? Is it possible that classical feedback can boost the capacity? And we mentioned these two different bounds. There was the last one, which is based on semi-definite programming. There was the entropy bound. How do they compare? We don't know the answer to that. Okay, with that, I will stop. Thank you for listening.